Alright, so I don't know exactly what my error was, but I'm back on track with the realistic value. So earlier I had this value, this 100,000. That's not correct. Ran it back through the calculator. I got about 66,940, which matches what I have on my computer screen a little better. So let's run these conversions again. So that's divided by 32.2. That gets me pound force per square feet. And divided by 144 gets me 2 psi. So this really should be about 14.44 psi. Again, that's pounds per square inch gauge. All right. So with that rectified, let's continue on here. This is page 2, and that's the answer then to part A. It's 14.44 psi. So part A was figure out what is the pressure required to maintain this flow rate, neglecting all losses. Let's find it now, neglecting the minor losses. That is, let's find this with the major losses in place. So we can go back here. All right, we'll rewrite this equation real quick. Okay. So where we started back on page 1, P1 gauge is going to equal the density times V2 squared minus V1 squared divided by 2 plus GZ2 plus the energy loss. Now in part A we said all the energy loss is going to be 0. For part B we're going to neglect the minor losses. So here the energy loss is only going to be the major loss. And that's what we just got through doing previously. Right, so this next homework assignment is going to include the minor losses. That's the next part of the problem. That's part C. Here let's just do the major loss real quick. I'm going to pull up a Moody diagram on my tablet. Had that pulled up on the break, and that's okay. Right? So, alright, because we are going to need a Moody diagram for this one. Okay, so I've got a Moody diagram now we can work with. Alright, so that's ready to go. Because that Darcy friction factor is going to be a function, as we've said before, of the Reynolds number, and if it's turbulent, epsilon over d. Well, we've got to figure out if it's turbulent first. Okay, now I've already looked up the viscosity, which I know I need because the Reynolds number is going to be rho v d over mu. So I've already, remember we looked up properties just a little bit ago, and we found properties of density and viscosity of water in English units at 50 degrees Fahrenheit. So we're good to go there. Let's just go ahead and get this right now. The Reynolds number, I've already computed this, so in the interest of time, let's just, I can at least write this out. 62.41 pound mass per cubic feet. I'm going to write this kind of quickly. We said V, so initially in the 3/4 inch section, this is 14.52 feet per second, and the diameter is 3/4 inch. That's 0.75 divided by 12 feet. Divided by the viscosity. I said the viscosity was 8.781 times 10 to the minus 4, and that is pound mass per foot and also per second, are the units on in that value there. Now again, have your calculator, run these through real quick. I'm giving you a little bit of time here. I'm getting about 645. So we'll say 645. I'm going to round these other two off because I'm going to the Moody diagram. It's like 19, 645, 19, and that comma goes there. Right, which we'll say that is 6.45 times 10 to the 1, 2, 3, 4. About 64,500. It's definitely turbulent. What was the transition value we talked about? Anybody? Anybody? About 4,000, right? Anything over 2,300 we'll assume turbulent. anything over 4,000, we're almost guaranteed to be turbulent. This is turbulent. This is 64,000. Very, very turbulent flow. Okay. So since it's turbulent flow, I also need to know the epsilon value. Well, if you go look up in your tables there, we said this is copper tubing. So the epsilon for copper tubing in English units, I've written down here to be let's just go look it up. I'm not sure I trust it. So go look that up real quick. Of course, when I need to find it quickly, I can't. It's a point, a bunch of zeros and an 8. I'm just not sure how many zeros. Getting 5 zeros and a 5. Okay, right. Yeah, so in feet, it's going to be 5 zeros and a 5 feet. So that's epsilon, at least in our tables, we're getting that for epsilon for copper tubing. So I need to know, I've got my Reynolds number now, and I need to know epsilon over D. I've computed that out to be in the 3/4 inch section 4 zeros and an 8, 0.00008 is epsilon over D. Okay, so given that Reynolds number and epsilon over D, I can now go find the Darcy friction factor using a Moody diagram. I have one here. Put ink on it. So we said 6.5 roughly times 10 to the 4. So this is 10 to the 4. Here's 10 to the 5. Got my stylus there. I just bumped my camera. Let's see how bad the alignment is. That's okay. All right. So 6 times 10 to the 4, roughly in here. Okay. And we said that epsilon over D is 4 zeros and an 8. I've got 4 zeros and a 5. I've got 3 zeros and a 1. So this is 00010. This is 00005. It's going to be in between these two, right? And it's going to be closer to this one. So if I'm going to try to hug this line, it doesn't really matter which one it's because it's between those. It gets kind of jumbled up in here. You can see. But pretty close to that line there, right in there. The Moody diagram is not exact. If you want an exact value, we need to use the Holland expression as a good approximation, and use the Colebrook to dial in an exact value. But I'm pretty comfortable with something on the order of about 0.02 to 0.021 with the Moody diagram. That might be a little bit high, but that ought to get us pretty close. Okay, so let's say F is in the neighborhood of 0.021. It's a little more than 0.02, and we're just going to specify so we know how the heck did we find that. We used the Moody diagram to find it. Okay? All right. We're good on time. Okay. So, what the heck are we doing? Oh, we're trying to find the energy loss, because we're trying to find the inlet pressure, right? So we need to find the energy loss to do that. I've now got F, I know L, I know D, I know V, I know everything. We're good. Okay. So, let's do this. Let's say P1 gauge is equal to, and I'm going to group these up. I'm going to say rho times quantity V2 squared minus V1 squared over 2 plus GZ2 plus density times the energy loss, or the pressure loss if you prefer. Now, why group these up? Well, I already know this one. We said just a second ago, this right here 14.44 psig, remember? We don't have to recalculate this. We just have to calculate this value. Okay? So you're welcome to recalculate the whole thing. I'm not going to. Just not going to do it. Okay? Alright. So let's do this. I'm going to find the energy loss first. This is page 3. Okay? So let's find the energy loss first, then I'll multiply by density. So the energy loss first, which is going to be F L over D V squared over 2. We've just found F to be 0.021 about. The length we said was 60 feet, if memory serves. Yeah, we said 60 feet. That's all through the 3/4 inch tubing, so that's going to be 0.75 divided by 12. You can convert that early on to feet if you like. I just didn't want to carry it around. We said the speed. What did we say the speed was? I said I did it on my spreadsheet and said that was about 14.54 feet per second. That's going to get squared divided by 2. Now I have this quantity, E over L. According to my spreadsheet here, I'm finding this to be about 2008.5. That's going to be feet squared per second squared, for whatever that's worth. Again, what we want to know is we want to find density times this energy loss. All right? And so that's going to be the 62.41, our density, pound mass per cubic foot. Multiply by this, we just found the energy loss of 2008.5 feet. And that's going to be feet squared per second squared, sorry. And I'm going to go ahead and do my unit conversions. We did them just a second ago, right? Remember, we divided by, we did this pound force to pound mass conversion of 32.2, and then we did 1 square foot for every 144 square inches. So let's go ahead and do that. Let's get rid of the pound mass. I've got pound mass up here. To get rid of it and get to pound force, I need for every pound force second squared, there's 32.2 pound mass feet. And then we get, that's going to leave me with pound force per square foot. So for every square foot, there's 144 square inches. And that should leave me with PSI here. Right? So the pressure loss, rho times the energy loss, which again is the pressure loss, I'm computing here. Now again, go ahead and do this on your own and double check this, because as we've seen, I can make a mistake. 27 point, we'll say 03 PSI, pounds force per square inch. P1, which we said was going to be the original 14.44 PSIG, plus now this quantity, this 27.03 PSI. They're both pounds per square inch. All right, so I've got this here. That number's already stored, so let's add to it the 27.03. It's actually 33 on my computer screen. Give it an additional digit there. All right, so I'm getting 41.47 PSIG for part B. Keep bumping my tripod here. There we go. So that's part B. Three-part problem. Again, we did part A in neglecting all losses. Part B, we've neglected the minor losses. Part C, in the next video, we're going to neglect no losses. We'll include the minor losses in the next video. Loud pop. I'll be right back.